Hello everyone, my name is Cunyang from Institute of Computing Technology, Chinese Academy of Sciences. The topic of my presentation is about an input-ware tuning framework for compact BLAS based on ARMv8 CPU. I'd like to divide my presentation into 4 parts: introduction, approach, experiments, and conclusion. So first is the introduction of compact GIM and TRSM. GIM and TRSM are two of the most widely used linear algebra subroutines in scientific computing. Compact GIM, compact TRSM means the batch processing for large groups of small-size matrices. Our interface divides this process into 3 steps. Firstly, converting the matrix A, B, and C into compact format. Secondly, the computation function will use this format in order to make full use of SIMD registers. And finally, converting compact format into a standard format. Although optimization for dense matrix operations has been well studied, this operation method is still not sufficient to obtain high performance on compact BLAS. First, small matrix is difficult to fully utilize the weight of the SIMD registers under traditional methods. Second, the edge processing causes many overheads for some metrics. Third, the small matrix can be stored entirely in L1 cache, making the original tiling methods meaningless. And finally, traditional methods like an input-ware tuning framework generate high-performance execution plans for small matrices of different size. For these problems, we propose IATF, an input-ware tuning framework to optimize large group of small GIM and TRSM on ARMv8 CPU. It contains the install time stage and the runtime stage. At the install time stage, it converts the matrix to the SIMD-friendly data layout and then generate highly optimized data packing kernels and computing kernels. We avoid pipeline bubbles through careful instruction schedule. At the runtime stage, it chooses an appropriate number of metrics for batch forming each time and chooses the optimal data packing kernel and computing kernel according to the input matrix properties. Finally, it links the above strategy into execution plans. In the following, I will explain our methods in detail. In terms of implementation, we have divided these solutions into these models. At the install time stage, the packing kernel designer generates data packing kernels for each data type and matrix properties. And the computing kernel designer generates computing kernels for each data type and different kernel sizes based on the abstracted templates. And the kernel optimizer optimizes the computing kernels to achieve optimal performance by optimizing instruction placement. At the runtime stage, batch counter determines the number of metrics for each GIM and TRSM operation based on L1 cache size and matrix size. Pack selector chooses the optimal data packing kernels or no data packing according to matrix properties. Execution plan generator selects the optimal computing kernels and combines the data packing kernels to generate an execution plan. Our design methods are based on SIMD-friendly data layout. For a group of metrics, SIMD-friendly data layout puts the same location of consecutive P matrix into a continuous area in memory, as shown in algorithm 1. It describes a simplified SIMD-friendly data layout-based GIM, and the NM represents the number of batch metrics. It shows that we can use vectorization instructions to process P matrix with the SIMD-friendly data layout. We abstract the typical computing patterns of GIM or TRSM as templates, then automatically generate the assembly kernel through the templates for the up-level functions to use. Automatic kernel generation can significantly reduce the workload of our approach. The main idea of finding the optimal kernel size is to minimize the CMAR, that's the compute to memory access ratio. In addition, we use ping-pong operation to avoid pipeline bubbles, that is, load the data needed by the next step in the current step. We also optimize the compute kernels for every possible size to obtain the consistent high performance of IATF at all sizes. For TRSM, we divide the kernel design into two modes based on the size of matrix A. First, when A is small enough to be stored all in registers, we can directly use the template described in ARMv8 to generate the computing kernel. Second, when A cannot be stored in the register, as shown in figure, the problem is divided into a triangular part and rectangular part. The triangular part can apply the template of ARMv8, and the rectangular part use the GIM kernel template. Our kernel optimization optimize kernels to minimize pipeline blocks, as shown in figure. The kernel optimizer will first reorder the instructions so that there is a large enough gap between two related instructions to eliminate pipeline block. The load instruction is then inserted between the calculation instructions so that the calculation instruction has load instruction delays. In addition, at the computation stage, matrix C is still in the memory. Thus, we use PRFM instruction of the ARM architecture to prefetch it at the beginning of the computing kernel to eliminate the risk of cache miss. Under the SIMD-friendly data layout, the primary purpose of data packing is to enable the computing kernel to continuously access matrix A and matrix B. Similar to the mainstream BLAS library, we adopt the strategy of N-shaped or Z-shaped data packing for the matrix, as shown in figure. No packing strategy is applied in the case where the expensive data packing overhead of small matrix can be saved, and the performance improvement of this strategy for small matrix operations is significant. The runtime stage is to select the optimal computing kernel and data packing kernel generated at the install time stage according to the input parameters to form an optimal execution plan. The batch counter decides the number of matrices for computing each time at the runtime stage according to the matrix size, data type, and L1 cache size. It needed to ensure the matrix is always in the L1 cache throughout the computation. For GIM, pack matrix A and B up to the size of L1 cache at a time, and reserve space for matrix C. For TRSM, pack matrix B and the triangular part of matrix A up to the size of L1 cache at a time. Pack selector choose the optimal data packing kernel to match the computing kernel according to the data type and matrix properties. It matches appropriate data packing kernels for different modes to pack matrix into the same order, so that only one computation kernel is needed to handle all modes. The execution plan generator choose the optimal computing kernel and combine the data packing kernel provided by the data packing selector as the cache strategy of the batch counter to form the execution plan. For large groups of matrix batch operation, the runtime stage overhead is not significant, since it only generates its execution plan at the beginning. We have done sufficient performance comparison tests to fully demonstrate the performance of IATF. We compare the IATF with OpenBLAS, RMPL, and libxsm. Run each kernel 100 times and take the geometric mean as the final result. To fully demonstrate each kernel, we evaluate the performance of square matrix of size 1 to 33 and initialize the matrix by filling it with random floating point numbers. This table shows the specification of two processors. The result demonstrates our strong performance of compact batch gene for real or complex numbers in single pressure or double pressure under NN mode. For TRSM, we show more obvious performance advantages. In summary, we proposed a framework for complex BLAS, the IATF, based on SIMD-friendly data layout. This paper presents a series of data packing methods and kernel design methods for large group of small matrix, compact GIM, and compact TRSM to dramatically improve performance. We also propose an input-aware auto-tuning framework to select the optimal kernel according to the feature of the input matrix. The experimental result shows that IATF could achieve significant performance improvements in GIM and TRSM compared with other mainstream BLAS libraries. In the future, we will focus on the kernel design and optimization of other BLAS functions under SIMD-friendly data layout. In addition, we would investigate and extend our approach to multi-core CPU or GPU. That's all for my presentation. If you have any question, please feel free to contact us. That's all. Thank you.